Welcome to Geometry Chapter 11, Day 2, Volume of Prisms and Cylinders. Find the area of each of these figures, come back and check your work. Number 1, number 2, 3, and 4. If you had any issues, please see me. Today we're going to learn and apply the formula for the volume of a prism. We're also going to learn and apply the formula for the volume of a cylinder. What do these two figures have in common? Yes, two congruent parallel bases. We're talking about volume. The volume of a 3D figure is the number of non-overlapping unit cubes that you could fill that figure with. It would exactly fill the interior. Okay, so 1 by 1 by 1 unit cubes. Cavalieri's principle says that if two 3D figures have the same height and they have the same cross-sectional areas at every level, so this triangle is the same area as this triangle, and so on all the way up these two prisms, then you have prisms with the same volume. The volume of a prism with a base area, capital B, represents base area, and height of h is V equals the base area times height. So I imagine finding this area and then kind of just finding all the little cross-sectional areas like it to the top as you ascend, right, or as you descend, whatever. The volume of a right rectangular prism is unique because every side has an opposite congruent base, right? So any face could be a base. Volume then is length times width times height in kind of your everyday language, right? For a cube, that's even more special because every side has the same length, right? So to find the volume, we simply take the edge, take the length of the side, and cube it because each of the dimensions, length, width, and height are the same. Find the volume of this prism. Round to the tenths. Come on back. Okay, you should have 195 centimeters cubed. Find the volume of a cube that has an edge length of 15 and come back. Good, and you should have 3,375 inches cubed. Find the volume of the right rectangular hexagonal prism. Round to the nearest tenth. Pause and come back. Now the trick here was finding the apothem, right? And so you might need to find the number of degrees in all of these angles. It's 360 divided by 6, right? So these are 60-degree angles. 2, 3, 4, 5, 6. And so then we can make a little right triangle. So the base of that little right triangle would be 4.5, an apothem, and then we have the hypotenuse. That ends up being a 30, 60, 90 triangle, doesn't it? So that hypotenuse is 2a, 4.5 and 9, and then you simply find 4.5 times the square root of 3 to get that apothem. Okay, which is what they do for you here. Once you have that, in order to find the base area, you simply take the perimeter of that hexagon, right? 9 times 6, 36. And you multiply by the apothem to get each of those triangles and divide by 2. Okay, so we end up with, let's see, where do we have it? We end up with a base area of 121.5 times the square root of 3. This is left in radical form. Once we have the base area, we simply multiply by height. And when we do, we end up with 2,525.3 feet squared. Can you find the volume of a triangular prism with a height of 9 yards, whose base is a right triangle with legs of 7 yards and 5 yards long? Do it and come on back. Please start with your plan first each time. Volume equals base area times height. And then you have to say, what type of a base do I have in this prism? Triangular. So the base can be written as base times height over 2, right? Base area is base times height over 2. This is the triangle. Out here is the prism height, right? So we substitute the known information. 7 times 5 over 2 divided times 9, and you end up with 157.5 yards cubed. Notice I leave the units till the end because they were all in the same units. I could raise the difficulty level by giving you one of the dimensions in feet or something, and you would want to put those into the same units as the other two. Okay, tricky question here. We're asked to use this rectangular prism as a design for a swimming pool. Estimate the volume of water in the pool in gallons when it is completely full. So the density of water is about 8.33 pounds per gallon. So estimate the weight of the water in pounds. Two things. So estimate the volume in gallons, and we're given a conversion factor, and then the weight in pounds. We're going to have to use two conversion factors. So pause and go find the volume of the water. Okay, start with your plan. Length times width times height will give you the volume. Substitute the known dimensions, and we have the volume in feet cubed. We're asked to find the number of gallons, so we're going to use the conversion factor, right? So if we have feet cubed and we're trying to get to gallons, we're going to use this conversion factor, placing feet cubed in the denominator so that we can have feet cubed over feet cubed, right? And so when we do, it looks like we're dividing 3,375 by 0.134, which leaves us with a lot. It leaves us with 25,186.57. Scoot that over a little bit. 25,186.57. And I'm going to move this over a little bit for you to see it. And that now is in gallons, right? Geez. Whoops, went down what level? Can I get it to stretch over there? Let me stretch this box a little bit. Gallons. Oops. Let me just put G for gallons. Okay, it doesn't mean grams. I'm just not having an easy time fitting it in here. Good. So now that we have that, we've answered the first question, how many gallons, right? But we need to answer this weight question. So they give us a factor to use here. They say that the density of water is 8.33 pounds per gallon. Here's gallons. So let's convert that, right? And so if we have our answer in gallons, we're going to want to use the factor as it's set up here, right? So we're going to multiply the number of gallons. I wish they'd kept the units here so you can see that the gallons will end up in the numerator and denominator, so we will cancel them, right? And you're multiplying 25,186.57 times 8.33. And we find that the swimming pool holds a lot of pounds, 209,804 pounds of water. It's amazing how much a gallon of water weighs, huh? Cavalieri's principle for prisms also relates to cylinders. So if we have a right cylinder where we have a right angle with the base and the height, and a kind of tilted cylinder, as long as we have the perpendicular height and the base area, we find that the volumes could be the same. If they have the same base area and the same height, the volumes are the same. So find the volume of this cylinder. Give your answer in terms of pi, and then round it to the nearest tenth. Be sure to pause at each of these questions and come back. So the radius here is 9, right? That's the diameter, so 9 squared is 81. Pi is 81 pi for the base. R squared, pi r squared we got, times height, times 14. So we will find that we end up with 14 times 81 pi, right? Rounded to the tenths. There you go. Now what happens if we change the dimensions of a cylinder? Changing dimensions with volume can impact 3 different dimensions, can't it? So if the radius and height of the cylinder are multiplied by a factor of 2/3, what will that do to the volume? Well, we can actually find that here by multiplying these, the height and the radius by 2/3. Look how nice 3 will divide into these numbers, right? And we can find that it affects it by reducing the radius from 24 to 16, and by reducing the height from 33 to 22. Look at the impact on the volume. 19,008 was the original volume, 5,632. It's like a third of what it was. So by reducing the volume by this factor of 2/3, we end up having a dramatic effect on volume. Basically, the 2/3 is affecting the radius, which is squared, so 2/3 times 2/3, and then the height, right? Another 2/3 factor. So we can say that the effect that this factor has on volumes would be 2/3 cubed, right? Which equals 8/27. The volume is 8/27 of what it was. Interesting, which is about a third, isn't it? Okay, so what about if we double the length, width, and height of a prism? What do you think the effect will be on volume? Doubling, doubling, and doubling. And I'm sure you guys have this because you've seen things like this already. You're going to affect this by 2 to the third, right? You're adding a factor of 2 on each dimension, and 2 to the third is 8. If the original volume was 18, it's been increased by 8 times to 144. Composite figures. The important thing to know with finding the volume of composite figures is plan. He who fails to plan plans to fail. So you need to make a beautiful, wonderful, fabulous plan. And the way I like to see these plans is, I'm sorry, I'm doing surface area with 7th grade. Volume equals, in this case, the volume of the little triangle. Let me see if I can do a subscript. I'm going to put TRI. I hope it's typing. Let's see what happens when I come back here. Yeah, the volume of the triangle. Let's see if I can move over. Oh. Okay, so here we have it. The volume total is the volume of the triangular prism plus the volume of the rectangular prism. So please start with a plan. Once you have that basic plan down, you can come and write the volume plans for each of the individual pieces. So the triangular prism would be its base area times height, right? Plus the rectangular prism, its base area times height. The next step would be to say the total volume equals, how do you find the base area of a triangular prism? You got it. You are hopefully substituting the triangle, right? BH over 2, right? And then we would add, how do you find the base area of a rectangular prism? It's simply base times height, isn't it? And, whoops, come on, let me get back in there. And so, because it's a rectangular prism, we could also use the length times width times height formula, right? And now we substitute the known values here. So go ahead and do that and come back and see what you got. The tricky figure is the prism. We're not given the perpendicular height. You had to go find that. Knowing that this is an equilateral triangle, we simply had to find the height using our 30, 60, 90 knowledge, right? And when you do, you can plug that in with a base of 8, and ta-da, the total area is 270.9 centimeters cubed. Great. Okay, so make sure that you make a plan. Make a big plan and step by step fill it in with the sub formulas. So big plan with sub formulas like we did here. Big plan, sub formulas, and then substitute the information you need. You may need to go hunt some down, and you should be able to get to a successful conclusion here. Okay, pause, come back and check your work. And you should have these values. Good. And here, a cylinder with a base area of that. That has that volume. A cube. And I like this composite figure. I call it a donut. It's a large cylinder, take away a small, and there you go. Have a good time.